I would like to start first so us, the whole group here, everybody that's on this paper, we're quite new to computer science education. And this work I'll be presenting here is part of a project that we recently went through about introducing logic not only into computer science education, but very early on as one of the first things, as you could see, a first year course in logic. And in particularly, this is about an app which was developed as part of this project to help aid introduction to formal reasoning. So a little bit about the project, as you can see here, it's called LogTech EDU. This link is clickable. I'll give out the slides at some point. I should figure out how to do that. So you could click on this link and look at the project, what's been done so far there, and the members of it. But in particular, what we're interested in is development and use of educational logic-based software tools. So not just tools for teaching logic, but tools based on logic. And expansion of logic in the undergraduate curriculum, which has actually, and so at least at the JKU, this is something that's been moving in the past couple of years to actually add more logic at lower levels and also increase the use of logic in the education in the higher levels of curriculum as well. But most importantly, especially concerning the introductory course, is that we heavily use tools, so software tools to help the students and aid them through the course. So I'll give a little bit of an outline of the course in this talk. As well, I will focus on the tool that I helped develop, or was the main developer of, called AXolotl, which is specifically for dealing with inferential reasoning and helping students understand what logical proofs are, what proofs are in general. So at the end, I give a couple of slides concerning the experiment that was run and the results of this experiment and how they will lead to further investigation and, let's say, the extension of this project. So before I move on, just to put this slide here to give the motivation for this work and the motivation for this project, computer science and logic from the beginning were, it's part of the foundations logic, but it's decreasing in undergraduate university curriculum. But there's many applications of it, as I give some of them here as verification technologies and certain branches of artificial intelligence. It seems that logic is as important as it was back then as it is today. In our view, as I already mentioned, is logic is foundational CS and is not an advanced elective, and is why we were pushing this course. And it actually has been successful, and students actually really like this course as much as they like the programming courses that they take at the same time with it. So what are they introduced to? One thing is they're not introduced to deeper aspects of mathematical logic, but more they're introduced how they could use logic as a language to view problems that they're dealing with in CS. So this is part of the idea of encoding problems in SAT and SMT. And they're given an introduction to this formal language and the syntax and semantic separation so they could understand things in this more abstract way. Of course, this is all much lower. This is not as abstract as you would have it in advanced, let's say, junior level course, but it actually at least gives them an idea of how these things work. All right? And we use many educational software. Some I don't talk about here, such as Theorema. If anybody's interested, you could ask me about it later, or RISC-AL, which is a language for dealing with algorithms. All right. This could be found on the course webpage. Let's see if this mouse works. Yes, the course webpage. You can find some of this material there. So what is the course structure? So the course has first propositional logic, satisfiability, and then first order logic. For people who know what these concepts are, these are more advanced. So this is the more advanced concept, first order logic. And then finally, SMT is a mixture of both. The interesting part about the course is that every week there is a mini test. And every week there's weekly challenges, which will give you bonus points for the mini test. And every single module has at least one lab. First order logic being longer has 2. But all of this is optional. So even though the students are given some exercises, they don't actually have to turn it in for grades. So actually the only thing they're being graded on is the mini test, all right? But the optionality of these weekly challenges and labs helped us build this experiment I mentioned later. And AXolotl is the app that I will talk about in more detail now. Here's the Google Play link. So when they have the presentation, you could click on it. And also the code is open source, so you could find it on GitHub. So what is it? It's an Android app developed to aid students through formal rule application and proof construction, specifically for quantifier-free first-order logic. And it's a work in progress. It's at the level where we could try it in a classroom, but it it's still being developed further. And this is part of the ongoing effort on our part. What do you do in AXolotl is that the educator can make these kind of things called AXolotl files, which give problems to the students. And the educator can give them particular rules to use that they could manipulate the problem and get to a solution. Whatever the solution for the problem is, this is defined by the educator. Some examples of rules, things that you might be familiar with: associativity of operator, we have here; implication for those who know logic; proof by contradiction. And also you have this axiom rule, which is the basic rule of a logical system. And variables here just, they replace expressions, or expressions replace variables, and that's how the rules are applied. What does an AXolotl file look like? Just so you get a basic idea, it's just this here. You define what function symbols, what variables you have, and you define a set of rules. The set of rules could be anything that the educator wants the student to use. So in this case here, I stuck to the rules of some normal logical calculus. In other cases, you could do something completely different. You could just say, I want to test them on algebraic properties or something else. And also the problem could be with any syntax that you would like. It's outlined inside of on the GitHub repository what exactly you could do with it, and also in other papers concerning this app. So I give a little bit of a picture of what it looks like, AXolotl in action. Here you have the opening screen, you have the menu here. You could load problems, you could save a picture of your solution. You have a list of different types of problems you could do. The app comes with a library of about 70 problems in it. This here is the problems for classical logic. The students would be given a screen like this here, where you have the problem and you have a set of rules underneath that could be applied. In case they don't want to read it in this compressed form, you could open it up in this rule display, which shows it in a more pretty print form. This is the input that the students could do to make up new terms that replace the holes. This black hole and this white holes could be replaced by these terms. And we have this screen here, which is shown to the students to show them how the rules applied step by step in the whole process of applying the rule to the current state of the problem. And in the end, students would get something like this, where you have the rules that were used and the proof that they constructed underneath. I'll come back to this slide to explain a little bit more for the experiment. So concerning the experiment, what we did was we designed a lab, which I have in the appendix in case anybody has a question about it, for inferential reasoning and natural deduction. Students don't know natural deduction at this part of the course. They only know decompositional reasoning. What is decompositional reasoning? It is precisely what you see here where I put the mouse pointer. So all you do is you just shift around the symbols. You don't do anything else. You just remove this implication and you get the two variables on top. Students are used to seeing this, and they just used to saying, I apply the rules in just ad hoc, or I could just do it anyway and it'll work out eventually. Inferential reasoning is a little bit more difficult because you have to think about how to apply the rules often. Right? So because the labs are optional, we use this as a way to create a control group and a test group. So many students, they do well in the first module, so they're not incentivized to participate. So our test group was mostly well and poorly performing students. So what our hypothesis is that we have this mini test on decompositional reasoning, but those who participate in the lab will do better on the inferential reasoning mini test than those who didn't participate in the lab, and particularly for poorly performing students. So we believe this would help the poorly performing students will do better in the future. And what we call poorly performing is between 40 and 60%. We didn't count the lower part, the less than 40% on the previous test, because usually these are the students that are going to drop out or are not doing well enough anyway. They don't understand enough material. And this group, it takes a significant portion of those students that will possibly do better. So as the experiment, we had 213 students in the control group, 23 in the test group. We reduced that to the poorly performing, which is 62 students in the control group, 11 in the test group. So our experiment verified the hypothesis, but a very low significance. But in particular, I wanted to point out here, I see almost out of time. So I wanted to point out that when we look at how students that did perfect on the next mini test, then we saw a significant difference. So 45% of the test group did perfect on the next mini test, but only 27% of the control group doing perfect. So somehow some students really got it based on this software. So while it didn't verify the hypothesis' desired level of significance, it points towards the need for more investigation. Also, it's hard to measure the impact of this, even though students really like using the software, because we use other ways of teaching inferential reasoning as well. And the low participation in the lab might have affected the statistical significance. So feel free to contact me by email. I just put another email. I don't know what email I put into the registration, but this is another one you could contact me with. And if anyone has questions about the lab assignment, I have it here. So I could put these slides up. So, okay, a little bit over time, but yeah. No, thank you.